Dampers on transmission lines are devices specifically designed to mitigate or reduce vibrations in overhead conductors caused by environmental factors such as wind. Vibrations in transmission lines, if not controlled, can lead to premature aging, fatigue, and failure of the conductors, hardware, and supporting structures. In this detailed explanation, we'll cover the types of vibrations, how dampers work, the types of dampers used, and the importance of dampers in transmission networks. Vibrations on transmission lines. Before discussing dampers, it's important to understand the various types of vibrations that occur in overhead transmission lines. Aeolian vibration. Aeolian vibration is caused by low speed, steady winds between 2 to 12 meters per second flowing perpendicular to the transmission line. As wind flows past the cylindrical surface of the conductor, it causes alternating vortex shedding, which leads to conductor vibration. Characteristics. Aeolian vibration occurs at relatively low amplitudes 1 to 2 conductor diameters but high frequencies 5 to 150 Hz. This can result in fatigue damage to conductor strands, especially near clamps or hardware. Galloping is caused by ice or snow buildup on conductors, leading to aerodynamic instability. The wind flows over the ice-coated conductor, creating lift that causes large, low-frequency oscillations. Characteristics. Galloping results in large vertical and horizontal motions up to several meters and low frequencies 0.121 Hz. This can result in phase-to-phase or phase-to-ground short circuits. Subspan oscillation. It occurs in bundled conductors when wind causes oscillations in individual conductors between spacers in a subspan. Characteristics. These vibrations are lower in frequency and amplitude than Aeolian vibration but can cause wear at the spacer locations. What are dampers on transmission lines? Dampers are mechanical devices attached to the transmission line conductors to reduce or absorb the energy from these vibrations, thereby minimizing conductor motion and preventing damage. Dampers are usually installed at specific intervals along the transmission line, particularly near suspension points towers where stresses are highest. How do dampers work on transmission lines? Dampers work by absorbing the mechanical energy of the vibrating conductor and dissipating it as heat or redirecting it into the mass of the damper. The working principle is based on providing a counteracting force that reduces the amplitude and frequency of the vibrations. There are several physical mechanisms involved. Dynamic absorption. Dampers typically have a weighted mass connected to the conductor. As the conductor vibrates, the mass of the damper moves out of phase with the conductor's motion. This movement causes the damper to absorb energy from the vibration and convert it into heat, thus reducing the vibration amplitude. Tuned frequencies. Dampers are often tuned to specific vibration frequencies. For instance, dampers designed to reduce Aeolian vibration are tuned to respond to the high frequencies generated by wind-induced oscillations. This ensures that the damper is most effective at reducing the particular type of vibration affecting the line. Damping via friction. Some dampers work by generating friction between components. As the conductor vibrates, parts of the damper slide or compress, converting the vibration energy into heat through friction. Types of dampers. There are various types of dampers used on transmission lines, each with different designs and mechanisms to address specific types of vibration. Stockbridge dampers. Vibration dampers. The Stockbridge damper is the most widely used type of damper for Aeolian vibration. It was invented by George H. Stockbridge in the 1920s. Stockbridge dampers consist of two small masses, usually metal weights, attached at each end of a short length of steel strand cable. The steel cable is clamped to the conductor. Working principle. The damper works by oscillating out of phase with the vibrating conductor. The masses at the ends of the steel cable move, absorbing the vibration energy and dissipating it as heat in the damper's flexible strand. Application. Primarily used to control Aeolian vibration. Multiple dampers may be installed on long spans or high-tension lines to reduce the risk of fatigue damage. Spiral vibration dampers. Spiral vibration dampers are designed to control subspan oscillation in bundled conductors and light Aeolian vibration. They consist of a spiral-shaped rod wrapped around the conductor. Working principle. The spiral rod absorbs vibrations by providing mechanical resistance to the conductor's motion. It reduces low-amplitude Aeolian vibrations and dissipates energy as the conductor moves against the spiral. Application. Typically used on fiber optic cables and small-diameter conductors.
Tuned mass dampers. Tuned mass dampers are devices with a mass attached to the conductor via a spring or flexible element.
They consist of a small mass suspended from the conductor by a flexible material like a spring or cable. Working principle: the mass moves in opposition to the conductor's vibrations, damping them by converting the mechanical vibration energy into heat or internal friction. These are usually tuned to specific vibration frequencies. Application: can be used for both aeolian and subspan vibration damping. Pendulum dampers are used to control large, low-frequency vibrations like galloping. These consist of a pendulum or mass hanging from the conductor. Working principle: the pendulum swings out of phase with the conductor's galloping motion, reducing the amplitude of the oscillations. Application: installed on conductors prone to galloping due to ice buildup. Interphase spacers. Interphase spacers are used between phase conductors in areas where galloping is a concern. These are mechanical devices installed between conductors of different phases to prevent phase-to-phase contact during galloping. Working principle: the spacers physically separate the conductors and absorb some of the energy from galloping, reducing the risk of faults or conductor clashing. Application: commonly used in areas with severe icing or galloping risk. Importance of dampers in transmission networks. The proper application of dampers in transmission lines is critical to maintaining the reliability and longevity of the infrastructure. Here are key reasons why they are important. Prevention of fatigue damage. Aeolian vibrations cause repeated bending and stress concentration at suspension points, clamps, and hardware attachments. Over time, these repeated stresses lead to fatigue damage in conductors, causing broken strands or hardware failures. Dampers significantly reduce this risk by controlling vibration. Reduced maintenance costs. Dampers help to extend the lifespan of conductors, clamps, insulators, and other line hardware by preventing wear and tear from vibrations. This reduces the frequency and cost of maintenance, as fewer conductor repairs or replacements are needed. Improved reliability. By minimizing conductor motion, dampers reduce the risk of faults caused by mechanical wear, breakage, or short circuits, particularly in galloping situations. This increases the overall reliability of the transmission system. Mitigation of galloping, which can cause severe mechanical stress and even result in line clashing or short circuits, is controlled using specially designed dampers, e.g. pendulum or interphase spacers. This is crucial for preventing power outages in regions prone to ice storms or heavy winds. Energy efficiency. Reduced vibration also means less mechanical loss in the system. By preventing unwanted movement in conductors, dampers help maintain the efficiency of the transmission line and reduce energy losses due to conductor motion.